Welcome, Complex Zeros and Descartes' Rule of Signs. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is a lecture for Math 1508 Pre-Calculus at UTEP. Chapter 2, Polynomial and Rational Functions, comes from Larson's 10th edition of the Pre-Calculus text. This is section 2.5, Zeros of Polynomial Functions. In part 1, we looked at the rational zeros theorem. Here in part 2, we're going to look specifically at complex zeros and Descartes' rule of signs. So a couple of facts to get us started. First of all, complex zeros always occur in conjugate pairs. If f of x is a polynomial function with real coefficients, and if a plus bi, didn't mean to move that around on you. But if a plus bi is a complex zero of the function, then we're guaranteed that a minus bi is also a zero of the function. Always come in pairs. Think about the quadratic formula. You know that plus or minus going on? Yep, they always come in pairs. So, factors of a polynomial. Every polynomial of degree n greater than 0 with real coefficients can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. This is going to help us in a variety of ways. We're going to see this again with partial fraction decomposition, one of my most favorite topics in all of algebra that will be useful again in calculus. All right, so linear and irreducible quadratic factors. So let's find a polynomial. Let's start basic here. Look at this conjugate idea. Find a polynomial with real coefficients that has the given zeros. If we know 4 and negative 3i are zeros, well, we know that complex zeros always come in conjugate pairs. So if negative 3i is a zero, so is positive 3i. Zeros become factors, right? The x equals 4 becomes x minus 4 as a factor. X equals a negative 3i becomes the factor x plus 3i. X minus 3i also a factor. When I multiply these out, I would multiply my conjugate pairs to get x squared plus 9. And then I would multiply by the x minus 4 to simplify and get x cubed minus 4x squared plus 9x minus 36. If I have given zeros of 4, 3, and negative 2i, I know that the conjugate, positive 2i, must also be a zero. I turn my zeros into factors. My polynomial, I'll put an f of x in front of it. I would multiply my conjugates and get x squared plus 4, and then multiply by x minus 3 and take that result, and multiply by x minus 5, and we'll get our polynomial x to the 4th, right? 1, 2, 3, 4, makes sense. X to the 4th minus 8x cubed plus 19x squared minus 32x plus 60. I'm not going to lie, I did not do that by hand. I love my TI-89 as it does symbolic manipulation. I believe that Inspire does as well, along with several other Casio and HP products. So if my zeros are negative 5, and 1 plus I squared to 3, I know the conjugate, 1 minus I squared to 3, is also a 0. X plus 5 and x plus 5, right? Because I have negative 5 listed twice, so I'll have two factors. X minus 1 minus I squared root of 3 and x minus 1 plus I square root of 3. Remember my factors. X minus 1 minus I square root of 3. I will distribute this negative to get my last term. Similarly for the 1 plus I square root of 3. Polynomial, I'll put an f of x in front of it. And yeah, there's absolutely no way I would do that by hand. I used a TI-89 to get my overall polynomial. There are many different ways you could do this if you use some online tools. Or leave it in factored form. Factored form's nice also. Descartes' rule of signs. So let f of x be a polynomial with real coefficients, and it has to have a constant. So you can't have just ending with x, a linear term. You have to have a constant for Descartes' rule of signs. So the number of positive real zeros of f, is either equal to the number of variations in the sign of f of x, or less than that number by an even integer. The number of negative real zeros of f is either equal to the number of variations in sign of f of negative x, or less than that number by an even integer. And why is it less than by an even integer? It's because we're talking about real zeros here. And if they're not real zeros, then they're complex. And complex zeros come in pairs, 2 at a time. So a degree 3 polynomial could only have 2 complex numbers. So it could have 3 real zeros, or it could have 1 real zero and 2 complex. But it couldn't have just 1 complex and 2 real, right? Can't do that because complex come in pairs. So let's use Descartes' rule of signs to determine the possible number of positive and negative zeros of the function. If h of x is 4x squared minus 8x plus 3, this is a positive 4, a negative 8, and a positive 3. So from positive to negative is 1 sign change. From negative to positive is 2 sign changes. So I know there are 2 positive real zeros or no positive real zeros. So either all of them or none of them. If I replace h of x with h of negative x and I simplify, I'll have all 3 are positive since there's no sign change, no negative real zeros. For f of x equals negative 5x cubed plus x squared minus x plus 5. Taking the polynomial as is, I'll have negative, positive, negative, positive. So that's 1, 2, 3 positive real zeros, or 1 real zero. And f of negative x, once I substitute a negative, I will have all positive, and so there are no sign changes, no negative real zeros. Why do we care? Well, think about it. The rational zeros theorem, which we saw in a previous lecture, tells us all possible rational zeros. Now, Descartes' rule of signs will tell us if we're looking for positive ones or if we're looking for negative ones. If it says there are 2 or 0 positive real zeros and you've already found 2 of them, you're done. You know that you can move on. So Descartes' rule of signs is very helpful in eliminating possibilities. We also have an upper and lower bound rules. Let f of x be a polynomial with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. Now, if c is positive, so x minus c, it'll look like x minus 3 or x minus 17, whatever. And each number in the last row of synthetic division is either positive or 0, then c is an upper bound for the real zeros of f. Meaning, you don't have to look any higher than the c value you've already found. If c is less than 0, so x minus c would look like x plus 3, right? X minus a negative 3, so it looks like an x plus factor. And the numbers in the last row of synthetic division are alternately positive and negative. Zeros count as whatever you need them to. Then I found a lower bound for the real zeros of f. So I don't have to look any lower or any further to the left. So let's just verify some upper and lower bounds of the real zeros. If I have a function here, x cubed plus 3x squared minus 2x plus 1, I'm going to see if x equals 1 is an upper limit. So I'm going to divide by 1 using synthetic division with 1, 3, negative 2, and 1, my coefficients. Synthetic division, remember we drop the first number, multiply by 1 to go up and over. 3 plus 1 is 4, multiply by 1 to go up and over, add straight down. Multiply by 1, add straight down. Notice how the results are all positive. So we know that none of the zeros are bigger than 1. We also know at the same time the remainder was not 0, so x equals 1 is not a 0. Just there's nothing bigger than 1. I'm going to start looking at fractions and negative values. Let's see, is negative 4 a lower bound? I'm going to do synthetic division by negative 4. My results in the bottom row are 1, negative 1, 2, and negative 7. My bottom row alternates sign, so x equals negative 4 is a lower limit. And from our rational zeros theorem, we know that P over Q, all rational zeros, have the form plus or minus 1 over plus or minus 1. And that's plus or minus 1. So if 1 is an upper bound, but it doesn't work, right, because that's not a zero remainder, the only other thing I would check for a rational zero would be negative 1. And looking at sign changes, that's positive to positive, that's 1. 2 sign changes, I'll either have 2 or 0 positive real zeros. As it turns out, I'm not going to have any positive real zeros. I have 1 negative real zero, and I'll have 2 complex zeros, and I know this without even checking yet. Let's do it again. For f of x equals 2x to the fourth minus 8x plus 3. Is 3 an upper bound? Well, when I do a synthetic division by 3, bottom row is all positive, so 3 is an upper bound. When I do synthetic division, it's a lower bound by negative 4. My bottom row alternates. So between negative 4 and 3 should be all of my zeros. All possible rational zeros. Let's make this a little bigger. We'll come back to it when we need to. All possible rational zeros. The factors of the constant term, which was 3, are 1 and 3. The factors of the leading coefficient, which was a 2, are 1 and 2. All my fractions are 1 over 1, 3 over 1. 1 over 2, 3 over 2, and it could be plus or minus. What do we know? I know that the original function has 2 sign changes, so 2 positive real zeros or 0 positive real zeros. F of negative x, when I substitute a negative x everywhere there was an x, there's no sign changes, no real zeros. So we know, first of all, if 3 is an upper bound but does not have a remainder of 0, I know 3 is not going to be a 0, so I can mark that one out. I know there's no negative real zeros, so I can eliminate the negative idea. And I've just taken from 8 down to 3 different possible zeros that I have to check. And if I can eliminate 8 down to 3, I'm much more willing to check the synthetic division on 1, 1/2, and 3/2 to see what's going on for this particular function. I'm going to bring this back down, and now my red marks are not going to make any sense whatsoever, but that's alright, we'll leave them on the screen. That's it for complex zeros, Descartes' rule of signs, and the little upper and lower bound theorem.